Hi class, this is 9.4. We are on our last section in chapter 9. So in the previous lessons, we described covalent bonds as electrons being shared between two atoms. However, electrons are often not shared evenly. For example, consider the simple molecule of hydrogen fluoride. The fluorine atom pulls the electrons more strongly than the hydrogen atom. So the electrons are, on average, closer to the fluorine atom than they are to the hydrogen atom. As a consequence, the fluorine atom has a small negative charge, while the hydrogen atom has a small positive charge. We show this by writing a delta plus, so this is a delta plus, this is a delta minus, and above the positive atom, and then we have a delta minus above the negative atom to indicate which has a stronger pull on the electrons. The lowercase letter delta, this is what that is. It's a lowercase delta. Greek letter delta, sorry. Alternatively, we can show this polarity by drawing an arrow pointing in the direction in which the electrons are being pulled with a small cross on the back of the arrow to indicate the positive end. We refer to this type of bond as a polar covalent. So this is more electronegative, this is more electropositive. The electrons are over here, they're not even in the middle. And we can represent that as either this or here. The arrow always points towards the more electronegative, and this kind of plus sign is where they are being taken away from. So how can we determine which bonds are polar covalent? To do this, we use a property called electronegativity, which was first described by Linus Pauling, an American scientist. Electronegativity is a measure of how strongly atoms pull bonded electrons. The electronegativities of the elements are shown in this table. The table conveys one of the most important ideas in understanding chemical bonding, and we're going to take a look at this. So notice the electronegativity generally increases from left to right across the periodic table. These are numbers that have no units, so they're just numbers, but they represent the electronegativity. This is consistent with what we already know from ionic bonding. Metals tend to lose electrons easily, while nonmetals tend to pull or gain electrons. The electronegativity increases as we go up a group or column on the periodic table. For example, iodine has a value of 2.5, while the elements above it, bromine, chlorine, and fluorine, have increasingly high values. Fluorine is the most electronegative of the elements, meaning it has the strongest pull for electrons. On the lower left-hand side, cesium and francium are the least electronegative, meaning they have the weakest hold on their electrons. Notice that this table doesn't include the noble gases. Electronegativity is a measure of how strongly atoms pull electrons in a bond. Since noble gases generally do not form compounds, they don't have electronegativity values. They actually do. Some of them do form compounds, but that's past this chemistry. If a metal atom bonds with a nonmetal atom, the electronegativity nonmetal pulls the electrons away from the metal, resulting in the formation of a positive and negative ions and an ionic bond. On the other hand, if two nonmetals equal electronegativity combined, the result is a pure covalent compound. Polar covalent bonds lie somewhere between purely ionic and purely covalent bonds. In fact, there is a continuum between purely covalent, two atoms that have equal electronegativities, and purely ionic. We measure just how covalent or how ionic a bond is by measuring the difference between the electronegativities of the two elements. As a general rule, bonds are classified this way. Covalent bonds have a difference in electronegativity of less than 0.5. Polar covalent bonds have a difference between 0.5 and 2, and bonds with a difference of greater than 2, those are ionic, considered ionic. So here's an analogy for a polar covalent bond. In this image, two dogs are pulling a rope. The big dog on the right has a much stronger grip on the rope. He could take it if he wanted to, and he keeps the rope close to him. Similarly, in a polar covalent bond like HF, the bond, like the bond shown here, the electrons are held close to the fluorine atom. If this bond breaks, the electrons will likely stay with the fluorine atom. In a polar covalent bond, the more electronegative element has a greater share of the electrons and therefore a slight negative charge. As we see in later sections, the polarity and the charge differences described by these simple rules have a huge impact on chemical and physical properties. So let's take a look at an example. I moved the page too fast. In order to, carbon has an electronegativity. Okay, so which bond is more polar, a CO bond or an FS bond? Show the direction of polarity for both bonds. So carbon has electronegativity of 2.5, while oxygen has a value of 3.5. The difference between these is 1.0, meaning this is a polar covalent bond. Similarly, F is 4.0 and S is 2.5. The difference between these is 1.5. The bond is also polar covalent. Because the difference is slightly larger in this case, we say that FS bond is more polar than the CO bond. The atom with the larger electronegativity has a slight negative charge, and the atom with the smaller electronegativity has a slight positive charge. We can show the direction of polarity using the arrow convention. Alternatively, we can show the polarity using the delta, the small delta with the positive or the small delta negative to indicate that. So that's where you can see the differences on these. Remember, the arrow is always pointed to the more electronegative. Polar covalent bonds have a tremendous impact on molecules' properties. Molecules with polar covalent bonds often exhibit an overall polarity called molecular dipole, sometimes called a net dipole or simply a dipole. A molecule with a dipole has one side with a slight positive charge, while the other side has a slight negative charge. As an example, let's consider one of the most important molecules in the universe, water. Water's dipole, that is the polarity of the water molecules. Water's dipole is a result of its polar covalent bond and its shape. In earlier lessons, we saw that oxygen is more electronegative. Excuse me. Sorry, all of a sudden I had to yawn. Okay, so we have these properties. So we have, let me start back again because I yawned. Water's dipole is a result of its polar covalent bond and its shape. In earlier lessons, we saw that water has a bent molecular geometry because of these two lone pairs on the oxygen atom. And since oxygen is more electronegative than hydrogen, the oxygen side of the molecule has a slight negative charge, while the hydrogen side has a slight positive charge. The polarity of the molecule depends on its shape, and the polarity of the molecule depends on the shape and the polarity of its bonds. If we add together the effects of all polar covalent bonds in a molecule, we can determine the net dipole for that molecule. I think I didn't skip a page here, sorry. So, if we add together the effects of all the polar bonds in the molecule, we can determine if there is a net dipole, meaning an overall dipole, a pull or a force on that from that molecule. Often this is done graphically by visual inspection. To see how this is done, let's compare these two molecules. So we have water and we have carbon dioxide. We want to find the net dipole, so we want to know if there's an overall pull on this, which will make the molecule polar. We add together the pull of each polar covalent bond. The net pull is away from the hydrogen atoms towards the oxygen. Water has a net dipole. So basically what this is saying is that these two are giving their electrons to the oxygen. So this side is more electronegative and these are electropositive, leaving these like slightly charged positive. The CO2 molecule also contains polar covalent bonds. However, this molecule has a linear geometry. So the two polar covalent bonds in opposite directions. As a result, the molecule has no net dipole. So what this means is that this is a polar bond and this is a polar bond. But if they are symmetrical, they cancel each other out. So it's as if you had somebody pulling here on a tug of war and they have the same equal power here. This never moves because they cancel each other out, is what this is trying to say. So you can have polar covalent bonds, but not have a polar molecule. The molecule over itself will have no net dipole, meaning it's just neutral. There's no charges anywhere. The electrons are not being pulled in an unbalanced way. Where water, it's unbalanced. The electrons are more over here and away from here, creating partially positive and partially negative sections on the molecule. So let's look at another example. Consider the structure of sulfur dioxide. Wait a minute, where is that at? Where's this one at? Hold on, sorry, a second. Sorry, I was looking at the tractors. I didn't even see it's right here. I put these together, by the way. I don't know why I didn't notice it. Okay, does this molecule have a net dipole? So because the sulfur atom has 3 electron sets around it, it adopts a trigonoplanar geometry. The sulfur-oxygen bonds are polar covalent. They have oxygen pulls the electron density away from the sulfur. The 2 oxygen atoms are pulling in partially, but not completely opposite directions. This is similar to 2 tractors pulling up a stump from the ground. If the tractors pull in the direction, so the sulfur-oxygen bonds are polar covalent, the oxygen atoms pull electron density away from the sulfur atom. The 2 oxygen atoms are pulling in partially, but not completely opposites. I know I just read this, but I had to pause for a second. This is similar to 2 tractors trying to pull a stump out of the ground. If the tractors pull in the direction of the red arrows, their combined forces pull the stump in the direction of the blue arrow, labeled as the net dipole. Similarly, the pull of the 2 oxygen atoms of sulfur dioxide combine to create a net dipole. So this is kind of giving an idea of with the tractors of what's happening with this molecule on the bottom. These are both pulling in separate areas, and it creates an unbalance. This is not balanced because there's more electronegativity on this side and partial positive on this side. So identify molecules with a net dipole practice. To determine whether a molecule has a net dipole, we first identify any polar covalent bonds using the table of electronegativities. Then, based on the shape of the molecule, we determine if the polar bonds pull together or cancel each other out. Let's consider 3 more examples. Based on their geometry and the table of electronegativities, which of these molecules have a net dipole? So let's take a look here. So if you were going to start this from the very beginning, you're given the chemical compounds. I want to start from the beginning. Draw the Lewis structures, evaluate the direction of the polar bonds. So if we look at methane, which is CH4, since carbon and hydrogen have very similar electronegativities, the bond in the CH4 are nonpolar, and so CH4 does not have a dipole. And it's symmetric. Remember, if it's symmetric, they're all pulling the same, and plus the values here are almost so similar that they're almost equal. The second molecule, which is BCl3, contains polar bonds. Because it is trigonoplanar, the electron pull of the 3 chlorine atoms cancels each other out, and there is no net dipole. So they're all going in 3 directions, but very symmetrical and very equally. And the third molecule, which is CH2F2, the 2 carbon-fluorine bonds are polar, creating a net dipole in the direction of the 2 fluorine atoms. So if they cancel, so first one, no polar bonds, there's no dipole. And there's no polar bonds because the difference between the C and the H is not large. Polar bonds in the middle one, but they all end up canceling each other out. It's like an equal tug of war, going 3 ways, but equally that nothing happens. And then in CH2F2, there are polar bonds. It's an unequal, it's unbalanced, and they're all being pulled towards the fluorine. How dipoles affect properties. The shape and polarity of molecules impact their behavior. For example, let's compare the properties of the 2 molecules we introduced in the last lesson, carbon dioxide and water. The 2 molecules are about the same size and have both polar covalent bonds. But because of their different shapes, water has a net dipole while carbon dioxide does not. Because of their net dipoles, water molecules experience an attraction for each other. This causes molecules to stick together closely. Water is a liquid at room temperature because of the attraction between these molecules. Water is also able to dissolve many ionic compounds because of charged particles, which are ions. They are attracted to the polar water molecule. On the other hand, carbon dioxide is a gas at room temperature because its molecules do not have a net dipole, and they do not stick together as tightly as water molecules do. In chapters ahead, we're going to look at these ideas in much more detail and see how the shape and polarity of molecules determine how they interact with surroundings. So let me explain what I just said. This is H2O and this is CO2. They are very similar in molecular mass as well. This is heavier than this one. So the heavier, what you'll see as a trend is that the greater the mass on a molecule, they tend to start taking on the shape of a liquid and a solid. However, water has a lower mass than CO2. It should be a gas at room temperature, just like CO2. What changes that is that the bent shape allows it to be attracted to other water molecules. So what do I mean? What this isn't showing you here is that the red is the oxygen. So it's partially negative here and it's partially positive. So if you see the water, the hydrogens on this side, which are partially positive, are attracted to the partially negative side of another water compound. And that's what keeps happening. This is partially negative, these hydrogens are partially positive, they're attracted, and all of these keep attraction. That creates this very strong attraction between them, which is why we have water the way we have water. It's because of this. The shape is bent, it creates an unbalanced, it's polar, creating this unbalanced of electron sharing, which creates a polarity, and that polarity attracts other water molecules to other water molecules, so they orient themselves in the way that they need to be attracted to the other water molecule. With gases, that's not happening. Gases want to stay far away from each other. There's no attraction because they're neutral, so they don't matter. They don't matter. They are not attracted to each other. They go on their day without interacting with another one. So let's take a look here. Polar covalent bonds. Atoms do not share the electrons evenly. We have a chart here which shows you fluorine is the highest electron, which means electronegative, which means this has the strongest pull on electrons to anything it's paired with, unless it's equal to itself, if it's bonded to itself. Oxygen is the next one, and then you can see nitrogen, chlorine are equal in the values, and then carbon and sulfur are equal, and you can see it goes through different values. Metals like to lose their electrons, so they tend to have low numbers, where nonmetals want to gain electrons, so that's why they have high numbers, to show just how much they're going to hold on to those electrons. Which bond is more polar, a CO or an FS bond? We did cover this, but FS bond is more polar. Arrow points towards the F and the FS, and towards the O and the CO bond. Which of these elements is most electronegative? So I'm just going to jump through, because once you know that fluorine is first and oxygen is second, that's what you kind of look for. You also look for nonmetals. It's a nonmetal, not a metal. So in this case, you can instantly push out potassium. Potassium is a metal, right? And you'd have to look at this one here. This is 2.0. It's still lower than oxygen. So basically, and silicon is up here at 1.8, so it's even lower. So you kind of start remembering these things, that fluorine is really electronegative, oxygen is the second. And once you know that, these are things that just kind of get stuck in your head the more you do this stuff. Which of these is the most polar covalent bond? Now, I'm not going to work this out. You just simply have to subtract one from the other and take the positive, so it's an absolute value. It doesn't matter which one you do, just make sure that the value, if you have a negative, for instance, make it a positive. That's the actual value. So this one's going to cancel each other out. It's an equal tug of war. We have these two, which will be a 0.5. We have carbon with nitrogen. So sodium subtracted by fluorine, nitrogen subtracted by fluorine. I'm going to say it's sodium by fluorine because this one's all the way over here. This one's over here, and it's probably going to be the wrong answer. I was completely wrong. Oh, most polar covalent. Let's see. Nitrogen and fluorine. Yeah, that's a 1. That's a 1, but why is this one? I have to say, hold on a second. Which of these is the most, oh, you know what? Sorry, this is a sodium, this is a metal and a non-metal. This is an ionic bond. Remember, anything above 2 is an ionic bond. See, even I forget at times. So yes, it's E. N is attached to F. Which of the following best describes a phosphorus chlorine bond? Well, first thing is we have to subtract one from the other. So we have a 3.0 and a 2.1. That's 0.9. So it's above 0.5. So it's polar covalent, but it seems to be I'm going to say it's slightly, with the Cl would be slightly negative. Why? Because it's got a stronger it's a larger value, so it's more electronegative than the phosphorus. The phosphorus would be slightly positive. And here's the net pull again. If this helps try and imagine what's going on when you're looking at compounds to determine. Molecular dipole is an overall polarity in which different sides of the molecule have slight positive and negative charges. You can have polar bonds and the compounds still not be polar because they cancel out. Okay, so fill in any missing formal charges. Let's take a look at this. Okay, they gave me the slide, but I don't see another slide. So this is something that's got to be worked out. If you work it out, we can go over it if you wanted to confirm it. But I didn't catch this, or else I want to give you guys everything that has answer keys, and I didn't catch that this one didn't have an answer key with it. Which compound is the most ionic? Remember, ionic is a metal and non-metal, so that would be magnesium oxide. Which of these has a net dipole? Again, this is where you'll have to try to calculate and then try to visualize with the tractor pulling what's happening here, and it is going to be A. Based on the polarity, which of these would be most likely to dissolve in water? So here's something. Like dissolves like. Polar molecules will dissolve in water because water's polar. Non-polar molecules will dissolve in a solution that's, I don't want to say any, but in a solution that's non-polar. So for instance, fats will go into fats, oils will go into oils. Water and oil don't mix. Look at salad dressings. So that's what these polarities and non-polarities do. So based on this, it's going to be A. A is going to be, why? Because we have an oxygen on here and hydrogen, so it's going to be electronegative on this side. This one, yes, fluorine has a lot, but however, it's symmetrical. So this is going to be nonpolar because they're all pulling and the tug of war is never going anywhere. This is also a nonpolar one. This is also a nonpolar one. So it's going to have the oxygen on here, which this is actually an alcohol, and that's going to make this one dissolve in, that's actually methanol, and it's going to dissolve in water. Draw Lewis structures for these, and based on the Lewis structures for these, which does not have a dipole. So I'm going to give you the answer, and you can see it's A. How many of these molecules contain a molecular dipole? Again, I'm going to just give you the answer, which is 2. So that should be able to tell you that there's 2 here. We already know CO2 does not, and water does. I can tell you methane doesn't, so you'll have to figure out between these which one it is. I'll give you a hint. This has a lone pair. That can also affect